Hello everyone. In this video, we will learn to determine if the given process is driven by enthalpy and or entropy given the sign of the change in enthalpy and entropy for the process. 2. Use the free energy change to determine whether the process is spontaneous or not in cases where enthalpy and entropy oppose one another. In the previous topic, we learned how we can use the delta S of the universe to predict the spontaneity of a reaction. According to the second law of thermodynamics, for a spontaneous process, the delta S of the universe, which is equal to delta S of the system plus the delta S of the surroundings, must be greater than 0. Based on this equation, we need to know the entropy change of the system and the surroundings to be able to predict the spontaneity of a reaction. In this video, we are going to define another thermodynamic function that can predict the spontaneity of a reaction. This new function is called as Gibbs free energy, and it is represented by capital G. Capital G is equal to H minus Ts, where H is the enthalpy, T is the temperature in Kelvin scale, and S is the entropy. Gibbs free energy is an extensive property and a state function. Similar to other state functions that we defined earlier, we are more interested in measuring the change in Gibbs free energy of a system or a reaction. The change in Gibbs free energy can be written as the delta G is equal to delta H minus T delta S minus S delta T. At constant temperature, we can say delta T is equal to 0, and the above equation will be reduced to delta G is equal to delta H minus T delta S. This is one of the most important equations in chemistry. Next, let us discuss how the change in Gibbs free energy, delta G, can predict the spontaneity of a given chemical reaction or process. According to the second law of thermodynamics, for a spontaneous process, delta S of the universe is equal to the delta S of the system plus delta S of the surroundings must be greater than 0. The delta S of the surroundings can be written as Q reversible of the surroundings divided by the temperature. That is, the heat absorbed divided by the temperature at which the heat is absorbed or released. And the Q reversible of the surroundings can be written as minus Q reversible of the system, since the heat lost by the system is exactly equal to the heat gained by the surroundings or vice versa. We have learned earlier that at constant pressure, the Q reversible of the system, that is heat absorbed or released by the system, is equal to the enthalpy change of the system. Therefore, the delta S of the surroundings can be written as minus delta H of the system divided by the temperature. Let us now plug in the delta S of the surroundings value into the second law of thermodynamics equation. The delta S of the universe is equal to the delta S of the system minus delta H of the system divided by temperature must be greater than 0 for a process to be spontaneous. Let us multiply both sides of this equation with T. If we do that, we get T delta S of the universe is equal to T delta S of the system minus delta H of the system must be greater than 0 for a process to be spontaneous. Here in this equation, we have T delta S minus delta H. If I multiply this equation with minus 1, I would get delta H minus T delta S, which is the delta G of the system. Let us therefore multiply both sides of this equation with minus 1. Minus T delta S of the universe is equal to the delta H of the system minus T delta S of the system must be less than 0 for a process to be spontaneous. And we learned earlier that at a constant pressure, the delta H of the system minus T delta S of the system can be written as delta G of the system, that is, change in free energy of the system. So, we can write minus T delta S of the universe is equal to the delta G of the system must be less than 0 for a reaction to be spontaneous. The same equation can be written as below without writing any subscripts. Minus T delta S of the universe is equal to the delta H minus T delta S is equal to delta G, which is less than 0 for all spontaneous reactions. If we do not write any subscript, what it means is we are talking about the system. This is the general convention that we use when we are representing a thermodynamic variable. So, according to the equation, for a process at constant temperature and pressure, the reaction is spontaneous if the entropy of the universe increases during the process or the free energy of the system decreases during the process. The change in free energy of a reaction combines the enthalpy change and entropy change of a reaction to predict the spontaneity of a reaction. In the earlier videos, we learned that each of these thermodynamic functions, that is delta H and delta S, independently could not predict the spontaneity of the reaction. However, taken together, they can predict the spontaneity of the reaction. This relation is one of the most important relations in chemistry with implications in biology and other fields as well. It is recommended that you remember this relation. Let us now summarize what we have learned in the previous slide. 1. The delta G of the system is equal to delta H minus T delta S. This must be less than 0 for a reaction to be spontaneous. If delta G is greater than 0, the reaction is non-spontaneous and the reverse reaction is spontaneous under those conditions. If delta G is equal to 0, the reaction is said to be at equilibrium, where the forward reaction and the reverse reaction both occur at same rate. Now, we have two different functions that can predict if a given reaction is spontaneous or not: the delta G of the system and the delta S of the universe. Next, let us learn how to calculate the delta G of a given reaction. Let us first write down the formula. Delta G naught is equal to delta H naught minus T delta S naught. This is the same equation that we learned earlier under standard conditions. According to the equation, if we know the enthalpy change, the temperature, and the entropy change of a reaction, we can calculate its free energy change. And from the free energy change, we can predict if the reaction is spontaneous or not. In the earlier video, we learned how to calculate the enthalpy change of a reaction from standard enthalpies of formation values of all the reactants and products. The delta H naught of the reaction is equal to the H naught of formation of all the products minus H naught of formation of all the reactants. The standard enthalpies of formations, that is H naught F values, are tabulated and will be provided to you. We also learned how to calculate the entropy change of a reaction using standard molar entropies of all the reactants and products. That is, the delta S naught of a reaction is equal to S naught of all the products minus the S naught of all the reactants. Alternatively, we can use standard free energy of formation values of all the reactants and products to calculate the free energy change of a given reaction. That is, the delta G naught of a reaction is equal to G naught formation of all the products minus G naught formation of all the reactants. The free energy of formation values, that is G naught F values of various chemical substances, are recorded and tabulated. These values will be provided to you. Here is a list of standard thermodynamic quantities. As you can see, the enthalpy of formation, the free energy of formation, and standard molar entropies of all the chemical substances are given. I want you to note the units of these quantities. While the enthalpy of formation and free energy of formation are expressed in kilojoules, the standard molar entropy values are expressed in joules. We need to convert them into kilojoules when we are doing calculations related to this equation. Let us now do an example problem. Using the tabulated values of standard molar entropies and enthalpies of formation, calculate the free energy change for the following reaction under standard conditions and predict if the reaction is spontaneous or not at the room temperature, that is 25 degrees Celsius. The given reaction is solid magnesium reacts with half a mole of carbon dioxide gas to form magnesium oxide solid and carbon graphite. The equation for the free energy change of this reaction under standard conditions is delta G naught is equal to delta H naught minus T delta S naught. We can calculate the enthalpy change of the reaction from the standard enthalpies of formation of all the reactants and products. The delta H naught of this reaction is equal to H naught formation of carbon plus H naught of formation of magnesium oxide minus H naught of formation of magnesium plus half times H naught formation of carbon dioxide. If we look at the tabulated values, the H naught formation of carbon is 0. For magnesium oxide, it is minus 601.6. For magnesium, it is 0. And for carbon dioxide, it is minus 393.5. If we do the math, we get minus 404.85 kilojoules. That is the enthalpy change of the reaction under standard conditions. Let us now calculate the entropy change of the reaction from the tabulated values of standard molar entropies. The entropy change of this reaction under standard condition delta S naught is equal to S naught of carbon plus S naught of magnesium oxide minus S naught of magnesium plus half times S naught of carbon dioxide. Let us now plug in the standard molar entropy values of all the reactants and products from the tabulated values, and if we do the math, we get minus 106.9 joule per Kelvin. So we now have the standard enthalpy change of the reaction and standard entropy change of the reaction. We can use these two values to calculate the standard free energy change of the reaction. Before we do that, let's take a look at the units of entropy change and enthalpy change. The units for enthalpy change are kilojoules, whereas the units of entropy change are in joules per Kelvin. Let us first convert the entropy from joules to kilojoules. The standard entropy change of the reaction would be equal to minus 0.1069 kilojoules per Kelvin. So, delta G naught is equal to delta H naught minus T delta S naught. Let us now plug in the values of delta H naught, temperature, and delta S naught. Kelvin and Kelvin gets cancelled, and if we do the math, we get minus 372.99 kilojoules. Since delta G naught is negative, the reaction is spontaneous under given conditions. Alternatively, we can use standard free energy of formation values of all the reactants and products to calculate the free energy change of the reaction. That is, the delta G naught of the reaction is equal to G naught formation of carbon plus G naught formation of magnesium oxide minus G naught formation of magnesium plus half times G naught formation of carbon dioxide. Let us look at the G naught formation values of all the reactants and products and plug in those values into the above equation. If we do the math, we would end up getting a similar number, which is minus 372.1 kilojoules. Let us now discuss the effect of temperature on the free energy change of a reaction and consequently on the reaction spontaneity. For a given reaction to be spontaneous, delta G naught, which is equal to delta H naught minus T delta S naught, must be less than 0. We now have 4 different combinations for the possible signs of delta H naught and delta S naught. Combination 1, the enthalpy change is negative and the entropy change is positive. In this case, the delta G naught is always less than 0. Therefore, the reaction is spontaneous at all temperatures, and the spontaneity of such reactions is independent of the temperature. In this case, both enthalpy and entropy are in favor of spontaneity. These kind of reactions are said to be driven by enthalpy and entropy. Case 2, the enthalpy change is positive and entropy change is negative. In this case, the delta G naught of the reaction is always greater than 0 and the reaction is non-spontaneous at all temperatures. In this case, both enthalpy and entropy are not favoring spontaneity. Case 3, the enthalpy change is positive and entropy change is also positive. If delta S naught is positive, then minus T delta S naught is negative. In this case, we want minus T delta S naught term to be bigger than delta H naught term, for delta G naught to be less than 0. And the minus T delta S naught term will be bigger when temperature is bigger, that is, at higher temperatures. In this case, enthalpy is not favoring the spontaneity, but entropy is in favor of spontaneity. These kind of reactions are said to be driven by entropy. Case number 4. Enthalpy change is negative and the entropy change is also negative. If delta S naught is negative, then the minus T delta S naught term will be positive. And we want the overall delta G naught to be negative. Therefore, the minus T delta S naught term should be smaller in magnitude, and the T delta S term will be smaller at lower temperatures. In this case, the entropy is not favoring the spontaneity, while enthalpy is in favor of spontaneity. These kind of reactions are said to be enthalpy-driven reactions. For the reactions in which the entropy change and enthalpy change have same sign, the reactions are spontaneous either at lower temperatures or at higher temperatures. The higher and lower temperatures are relative terms. What you need to understand is that there will be a temperature at which the reaction transitions from being non-spontaneous to spontaneous. In the next slide, we will learn how to find out the temperature at which a reaction transitions from being spontaneous to non-spontaneous or vice versa. Let us look at the reaction that we discussed a couple of slides ago. Solid magnesium reacts with half a mole of carbon dioxide gas to form solid magnesium oxide and graphite carbon. The enthalpy of this given reaction is negative. Therefore, we can say that it is driven by enthalpy, and the entropy of the given reaction is negative. Therefore, the entropy change does not favor the spontaneity, or we can say that this reaction is not entropy driven. As we discussed earlier, for this reaction to be spontaneous, the minus T delta S term must be smaller, which means T or the temperature must be smaller. Therefore, this reaction is spontaneous at lower temperatures and non-spontaneous at higher temperatures. Let's write that down. At lower temperatures, delta H naught minus T delta S naught is less than 0, or we can write delta H naught is less than T delta S naught. At higher temperatures, delta H naught minus T delta S naught is greater than 0, or delta H naught is greater than T delta S naught. So this means at a particular temperature, it transitions from being spontaneous to non-spontaneous. The temperature at which this transition occurs can be calculated by equating the delta H naught minus T delta S naught to 0. So the temperature T at which this transition occurs is equal to H naught over S naught. Let us plug in the values of H naught and S naught in this equation and do the math. H naught is minus 404.85 kilojoules. S naught is minus 0.1069 kilojoules per Kelvin. Kilojoules get cancelled. If we do the math, we get 3787.2 Kelvin. So this reaction is spontaneous below 3787.2 Kelvin and non-spontaneous above this temperature. At this temperature, the reaction will be at equilibrium.